going to continue in Chapter 9 with transformations. Our last lesson was on symmetry. Now we're going to look at quadratic equations and, for that matter, let's say quadratic functions, and all functions actually, to see how do we show a transformation. In this lesson we're going to look at a vertical transformation, which of course is up and down, and a horizontal translation left and right. At the conclusion of this, we'll be able to graph any quadratic function. Now that's a three-letter word that has very big implications, doesn't it? Any? Well, let's see about that. We'll check back later and see if we think we achieved that. 5 minutes. Okay, we're going to try to do this in 5 minutes. This is a review of how you determine symmetry by looking at the formula itself with regard, we'll see if we have symmetry with respect to the x-axis, the y-axis, and the origin. Or in some cases, none of those will apply. What do we look for? We try putting in, for the x-axis, a negative y and see if it remains the same or an equivalent equation. So if I put in a negative y, so as far as the x-axis goes, it's no for the x-axis, because there's no way that's going to be an equivalent to where we started. Then we'll try for the y-axis. This is where we put in a negative x, and we get y equals negative x squared. And actually that is equivalent, isn't it? Because the negative 1, that's the coefficient here, when we square it, becomes a positive 1. So we say yes with regard to the y-axis. And then we look at the origin. In this one we put a negative y in for a positive y and a negative x, and we know that's going to turn out to be a positive. So that's not equivalent. We're going to say no with regard to the origin. All right, how about this one? This, because this is squared and this is squared, whether I put in x or y, a negative x or negative y, it's going to be equivalent. This is going to be yes to both the x-axis and the y-axis. The origin, I put them both in at the same time, and it still is symmetric. So this one is yes to all. How about this one? When I put in, let's check for the x first. I put in a negative y, I end up with x minus 2y equals 3. This is no with regard to the x-axis. And if I try now for the y, I put in a negative x, I get a negative x plus 2y equals 3. And this is no with regard to the y-axis. Now I'll try putting a negative in for both the x and the y, and I get a negative x minus 2y equals 3. Again, there's no way that one is an equivalent equation, so this one is no with regard to the origin as well. So we struck out on all symmetry with this one. Now on to the lesson itself. We're going to be using some stand-ins for constants. This k is going to represent the y component of a certain pair of numbers. So the y coordinate, how are we going to change y? We're going to be subtracting this number k from our y coordinate. However, with a function, we always solve for y. Remember, with a function, we're thinking this way. Functional notation. This is representing y, and we read it as function f with input x. In order to use this notation, we have to have y all by itself here. So, although I am subtracting this constant from y, I'm going to transfer it to the other side, and it takes on the other sign. It's now whatever my operation is. What is my operation on this function? I'm squaring it. So my input is x, and I'm squaring it. Then I'm adding the translation. So if I've got originally the simplest possible version of a quadratic, I have a special name for these. I don't remember if we've talked about it before, but I like to call these the parent functions. And from these we can get any number of prodigy. We'll have the very simplest represent the parent, and then we're going to complicate it a little bit, adding things or subtracting things or multiplying things to our parent function. It's very important to know the parent function really well. So I recommend to you that you study y equals x squared until you are totally confident that you know how to graph it. With the parent function, y equals x squared, the vertex is always at 0, 0. And let's join the points. The vertex is at 0, 0. We've already studied the symmetry of this. We know that the line of symmetry, I'm going to get, what can I use for a different color? Okay, I'm going to have a line of symmetry, which for this function, this equation, is this vertical line at x equals 0, and we know that that is the y-axis. So what are we doing here? We're just getting you really well acquainted with the parent function. has its vertex at 0, 0, and it's symmetrical with respect to the y-axis, or the line x equals 0. That's our parent function. Now, suppose I want to look at some translation of this. So I'm going to draw another parabola. See how well I can do with this one. And you'll notice, well, you probably notice I'm not drawing the lines smoothly, but anyway, this parabola is very similar to this one. You'll notice this one, when I added 1, notice that these are 2 by 2 grids. To get to 10, it'd have to be 2, 4, 6, 8, 10. When I added 1 to x, I got a point y that was 1 above y equals 0. When I subtracted 1, I got the same thing, a y value, an output, that was 1. You'll remember that when adding 1 or subtracting 1 lead to the same output, I have an even function. So this is an even function, and I'm taking and dropping it down. Now let's see, what does this look like? Where is my vertex? My y is still 0. Excuse me. My x is still 0, but my y is, remember these are 2 by 2 grids, 2, 4, 6. It's a negative 6. So I've dropped the vertex down from 0, 0 to 0, negative 6. Or I have translated it, let's look at this word here, translated it down 6. This would mean that my k is equal to negative 6. So my equation here is y equals x squared. The shape has not changed. It's not wider or narrower. It has the same shape, but it's been translated down 6. Now, I'm recommending that you use your graphing calculator today, so why don't you stop right at this moment and go ahead and get your graphing calculator. One of the things I probably should have mentioned earlier is this funny looking V hanging over vertical. What I'm trying to do here is create an association with K. If we take that little section of K out of there, and you think of K now as always being the vertical, then when we're looking at the vertex, as being H, which is pretty clear, horizontal, and K, vertical, it'll make more sense to you. We've got H minus K, and that's the vertical shift, equals the absolute value of X. Well, we want to write it as a function, so we need to solve for y. And we'll have y equals the absolute value of x plus 3. And this plus 3 is the vertical shift. Over here I have the parent graph of an absolute value function. Remember, the parent graph is the simplest possible function associated with absolute value. In this case, we've got a vertex at 0, 0, a line of symmetry at x equals 0, with this one, y equals absolute value plus 3. What are we going to do? Here it would be without being shifted at all. Here it's shifted plus 1. This one is shifted plus 2. And this one is shifted plus 3. And if I draw that, use a red pen, here's that absolute value function. Notice it's got exactly the same shape as the parent graph, and its line of symmetry remains at x equals 0, but it has shifted upward 3 units. That's the vertical shift. Vertical shift is, I think, fairly easy to understand. K is the vertical translation. How many vertical units apart are the graphs? Y equals x, and why don't we draw that? I think I will draw that one in blue. I think I'll draw that one in blue. I'll draw this one in blue, and that would draw right here. This would be y equals x, just a straight line. For every 1 I increase x, we increase y1. For every 1 I decrease x, I decrease y1. Now, that, I guess we would say, is the parent function for a linear, right? The very simplest linear that we could have. Well, now I want to look at a linear graph. This is a linear graph. Both of these are to the first power. But I want to shift it. I'm going to shift it down 2. So it's going to look exactly like this one, only every point is going to be shifted down 2. So when I go to draw this, and please imagine that I'm drawing a straight line, that's what I want to do, that's exactly 2 units down. So we've gone down 2. How many vertical units apart are the graphs y equals x minus 2? Okay, so that's the one we just did. And y plus 2 equals x. I'm going to go to a different color again. Let's try green. Now, to make sense out of this, hadn't I better do this? Y minus k equals x. This one, and I will change my pen back. This one was y equals x plus k. My k was a negative 2. For the second one I'm trying to consider, back to green, I'm looking at a different version of the linear, not written in functional notation, but y minus k. Well, that would be y minus equals x. What would my k be here? In order for this to turn out to be positive, it must be a negative 2. So if I have a linear function, and it still has a vertical shift downward, 2, it's actually right here along the same line as I had earlier. Now I could show this another way too. I could transform this into an equivalent equation, right? I just would subtract 2 from both sides, and I'd have y equals x minus 2. On to a horizontal translation. Let me get my blue pen back. We're so familiar with this parent graph, aren't we? I'm hoping that you are memorizing this parent graph with its vertex at 0, 0, and its axis of symmetry at x equals 0. We go over 1 from the vertex, and the graph goes up 1. We go back 1 from the vertex, and the graph still goes up 1. This is characteristic of an even function, isn't it? I go over 2, the graph goes up 4. I go back 2, the graph goes up 4. How about 3? 3 away from the vertex, I'm going up 9. 3 away from the vertex in the negative direction, still going up 9. This is the parent graph, one that you should try to memorize. Now, we're going to deal with a horizontal translation. So let's start first with this in the place of the parent graph. What is h in this case? H is referring to my horizontal movement. So if it were at this location, what would you say h is equal to? 0. And if I put it here, what would you say h was equal to? 1. So my equation would be y equals x minus 1 squared. What if I moved it horizontally over here? Now I'd have x minus 2, and I'd square that. So you could play around with this a little bit with your graphing calculator, and your graphing calculator will show you the new position as you put something inside these parentheses. Now notice that when we're talking about, let me get my pen, when we're talking about shifting horizontally, we are inside the operation. We're not tacking something on after we've done the operation like we do with vertical translation. We're actually putting something right into the domain. The thing that is going to be squared is no longer just x. It's x minus whatever we want to do for a horizontal translation. Please notice minus. So if I have y equals x plus, let's look at this one over here, 6. That's the whole thing that's being squared. And my h must be a -6. It's easy to get screwed up with this because when you see +6, our minds, don't they do this? You want to move everything to the right 6. No, no, no. You have to remember it's minus whatever your h is. So if it says +6 inside the squaring operation, you're moving a -6. You're moving in the negative direction. What function is translated 3 units to the right of y equals the absolute value of x? Here we're back to a parent function that you are familiar with. Let's make sure I've got blue. I just want to draw it for us. Here's the absolute value of x. And you're imagining I'm drawing a straight line because you would draw a straight line. Too bad your teacher can't. Okay, what function is translated 3 units to the right? Now we're not going up and down, so we're not going to add something on to this function. Where are we going to make our change? Inside the operation. So we have got to, I'm going to change my pen. We have got to look at doing something inside absolute value. If we want to translate it 3 units to the right, that means our new vertex will be right about here. So that would be a +3. Our h would be a +3. So what are we going to do here? X -3. We have a +3, and we're always subtracting inside the domain. So let's see. I think I've already got this ready for us. Here we go. So what would it look like? Well, if I hadn't been shifting it, it would be right there. If I'd shifted it 1 unit to the right, it would be the absolute value of x -1, x -2, x -3. There it is. Graph the function above by using the parent graph. It's so much easier if you have memorized the parent graph. You don't have to do a table of values. You just look at your parent and you realize I just have to shift everything over 3. Let me graph that. I've got all the points in place. And it would just be a straight line right down here to a vertex at 3, 0, and a line of symmetry at x equals 3. Okay, so big difference with horizontal translations. You have to go inside whatever the operation is. The one we did earlier, we went inside the squaring with absolute value, going inside absolute value. Oh, that's it. We finished. See you in class.